Hey everyone, in this video I'm going to walk through a simple cryptography project where a client and a server securely exchange messages over a TCP using RSA and SHA256 hashing. The goal is to know how the server and client connect, establish a tunnel by exchanging public keys, send an encrypted message, and verify that the message has not been tampered with by comparing hashes. The concept of the project is based on a client-server architecture, where the server listens in a control port, creates RSA key pairs, and handles three main commands: connect, tunnel, and post. On the other hand, the client connects to the server, exchanges public keys, encrypts a message using the server's public key, and then verifies its integrity using SHA256 hashing algorithm. Now let's take a quick look at the code, starting with the server. So here in server.py at the top, we can see that we imported several Python libraries such as Socket for networking, RSA, and PKCS10AEP for public key encryption, plus SHA256 and hashlib for hashing. We also define host and control port as 8080, which is the TCP port where the server listens for initial client connections. Then we have our function to generate RSA key pair. It creates a new 1024-bit RSA key pair every time the server starts. It returns a private key and its corresponding public key so the server can decrypt incoming data and share its public key with clients. Then we have our RSA encrypt that takes a public key and some bytes, wraps the key in a PKCS10AEP cipher object, and returns the encrypted ciphertext. The RSA decrypt does the reverse. It uses the private key to decrypt the ciphertext and recover the original plaintext, and the SHA256 digest computes a SHA256 hash of the given bytes and returns the raw digest. Our handle client function is where most of the server logic lives. First, it prints out that the connection has been requested. Then it creates a new TCP socket for data on a random free port by binding the port 0 and listening. It then retrieves that random port number, sends it back to the client over the control connection, and then waits for the client to connect with this new data port. Once the data connection is established, the server expects to receive the tunnel command on the data socket. If the command is tunnel, the server sends its public key bytes to the client, then receives the client's public key bytes and imports them as an RSA key object. At this point, the tunnel is set up and both sides know each other's public keys. Next, the server expects the post command on the data socket. If it gets post, it reads the first 4 bytes to determine how many bytes of the encrypted message will follow, then receives the encrypted message in chunks until it has the full ciphertext. The server then decrypts the ciphertext using its private key, prints the decrypted plaintext, and computes a SHA256 hash on the plaintext. It then encrypts this hash using the client's public key, sends the size of the encrypted hash, followed by the encrypted hash itself, back to the client, and reports the hash value it's responding with. If the server does not receive post, it prints an error message instead. So finally, we're defining our main loop. It starts by printing the status messages. It generates its RSA key pair once, then it creates the listening socket on host and control port, and it begins waiting for incoming connections. Whenever a client connects, the server reads the first command on the control socket expecting connect. If it receives connect, it calls handle client to create the data socket, perform the key exchange, and process the encrypted message. If the command is something else, it prints an error and breaks out of the loop. Now let's switch to client.py. At the top, the client imports the same cryptography and hashing libraries and defines the host and ports as 8080 matching the server's control port. The helper functions are implemented in the same way as on the server, giving the client its own RSA keys and encryption decryption capabilities. In the client's main function, the program starts by printing out status messages and generating its own RSA key pair. It then creates a TCP control socket and connects it to the server's hosts and ports. After connecting, the client sends the connect command, followed by a new line. It then reads the server's response, which should start a data port followed by the actual port number where the server created the data socket. If the response is correctly formatted, the client parses that port number and prints that it is creating the data socket. Otherwise, it prints out an error. Next, the client creates a second TCP socket, the data socket, different from the control socket created previously, and connects this one to the server at host and the data port it just received. To start the key exchange, the client needs to send a tunnel command on the data socket. The client then receives the server's public key bytes, imports them as an RSA key, and prints that it has received the server's public key. After that, the client exports its own public key and sends it to the server over the data socket, completing the mutual key exchange and establishing the tunnel. Now, the client prompts the user for a message. If the user just presses enter, it defaults the message to hello. The client converts the message to bytes, prints what it's encrypting, and then encrypts the message using the server's public key with RSA encrypt. After sending the encrypted message, the client waits for the server's response. It first reads 4 bytes to know how large the encrypted hash will be, then loops to receive the full encrypted hash in chunks until it has all the bytes. Once the full encrypted hash is received, the client prints that it has received the hash, and then decrypts it using its private key with RSA decrypt. The decrypted result is a SHA256 hash string of the original message as computed by the server. Next, the client computes its own local SHA256 hash of the original message bytes. If the hash from the server matches the client's locally computed hash, then the client prints secure. If they differ, it prints compromised. This is how the client verifies that the message received and processed by the server was not modified in transit. Now let's run a quick demo so you can see the output. First, let's start the server by running python server.py. Here we see that it's starting the server, creating an RSA key pair, and it's awaiting connections. In a separate terminal, we run the client. As we can see, it's starting the client. It creates the RSA key pair. Yeah, it creates the data, like the control socket, the data socket, and connects to the server. It then prompts us for a message. We can just type hello or leave it blank and just press enter to get like the predetermined hello. Here we can watch the client show the encrypted message snippet, then received hash and computing hash followed by secure, since everything matches. On the server side, we can see the decrypted plaintext, the hash computation, and the response hash value. This completes the explanation and demo of this cryptography project using sockets, RSA encryption, and SHA256 hashing.